This is video 29 on MicroPython and the 8th video on LVGL 9 on a Raspberry Pi Pico. In this video, we connect an external rotary encoder to our Pico and integrate it with LVGL 9 to interact with the widgets on our Ili9341 display. We explain the wiring and provide a 3D printable mounting plate. We verify the rotary encoder with a quick test program. Finally, we provide a code review of several programs. For this effort, I continue to use the Pico MicroPython display baseboard with a Pico USB board, the 2.4-inch Ili9341 integrated display, and an external rotary encoder. The GitHub site contains the firmware for the Pico, Pico-W, and Pico-W, and the MicroPython code for this video. By the way, the site contains updated firmware files for the LVGL 9.3 version for the Pico and Pico-W. As this channel covers multiple small system solutions over time, please subscribe to stay informed and click like, as that really helps. Let's look at a quick demo of the test group encoder program on the 2.4-inch Ili9341 display. Well, just a quick word on what you will see. The LVGL input device with type encoder has special operating logic. This occurs with no additional coding. When the program is first started, the screen is in navigation mode. Turn the rotary encoder knob to set focus to a widget. You can turn it again to focus a different widget. The screen will only focus on widgets attached to the rotary encoder. Once you focus a widget, you can select it by pressing the rotary encoder switch. That widget is now in edit mode. Turning the rotary encoder knob now changes values or cycles through the widget's items. Let's run the program. This program has two slider widgets associated with the encoder. As I turn the rotary encoder knob, the screen indicates which widget is in focus by putting a blue halo around it. Okay, the blue halo is around the second slider widget. To select the widget, I press the rotary encoder switch button. The halo color becomes red, which provides feedback to the user. Now, when I turn the rotary encoder knob, the slider's position changes. By the way, I added the edit status label and set the slider styles. Let's operate on the other widget. By pressing the rotary encoder switch button, the encoder is back in navigation mode. We see the blue halo around the second widget. As the knob is turned, we can select the other widget. Then we press the rotary encoder switch button to select the second widget. As you can see, the blue halo is around the first slider. Meanwhile, we can turn the knob and now see values change. I can press the rotary switch, putting the slider back into navigation mode. Now I can reselect the other widget. You see the blue halo is around the second widget. I can press the knob, put it in edit mode. The encoder device is tracking each widget and its values. Very little configuration is needed to accomplish this, as you will learn in a few minutes. Now that we know it works, let's discuss the hardware and setup. An inexpensive 360-degree rotary hardware device with 3 I/O signals. The clock and ST signals provide interrupts for the encoder, and the SW signal is for the built-in switch. Typically, you configure the device so that it returns a value between the min and max inclusive setting, and each turn causes the value to increment or decrement a small amount. For example, I typically set the min to 0, the max to 5, and each turn changes the value by 1. The device is very affordable to purchase on a small breakout board with resistors, a male header, and knob, so it is easy to interconnect to microcontroller pins. I got the model KY-040 device that included the resistors and used a full step. I checked the retailer's pictures to ensure the device had the resistors. To wire the rotary encoder, I simply used 3 consecutive pins that were free on the Pico. I find it easier to work with devices that are firmly mounted. I created a simple plate for the rotary encoder that can be mounted with 3D screws. The STL file is available at my GitHub site. It prints on my 3D printer in 15 minutes. I searched and found a GitHub site that provides MicroPython drivers for generic rotary encoders. The author, Mike Teachman, provides the drivers and simple but very detailed explanations of the settings. I highly recommend reading through his write-up. Please download the driver files, then use Thony to drag the files to your Pico's flash drive. By now you should have this collection of files on the Pico. Let's test the wiring and the new driver files. Please open Test Rotary Driver Pi in Thony. And we'll bring up the Test Rotary Driver program. Here you can see I have the rotary driver. Next I have pin definitions for each of the signals. These are totally arbitrary and you can change them to values that suit your system. Notice I set up the rotary with a min of 0, a max of 5, and an increment of 1. Also, I configured the range mode as wrap, which will make sense in a minute. We will scroll down to see the remaining code. Alright, let's click the green run icon. There's no graphical aspect to this, it's all printing in the Thony, so watch it as I turn the knob. As I turn the knob clockwise, it increments. Notice if I go past 5, it starts over. That's what's called wrapping. The same occurs if I go in the other direction. If I go counterclockwise and go past 0, I start over with 5, 4, 3, 2, 1. So now we understand how range wrap mode works. Finally, let's test the switch button. Okay, pressing the button causes a message switched pressed to occur in the Thony. Okay, now that we know the encoder driver works, let's look at the 3 steps to set up an encoder in LVGL programs. First, we define the encoder INDEV and its read callback. The callback must provide values to the data variable, specifically the enc_diff and the state. Lastly, we define an encoder group. Here we attach any widgets to be controlled by the operating logic. Alright, let's go back and open up the test group encoder program and click the green run icon. Okay, we're ready to walk through the code. At the top of my program, you see the rotary driver file. That's this line. Next, you see the definition of the rotary encoder device, very similar to what we just saw in the driver. The only difference is I set the min to 0, the max to 100, and the increment to 20. Moving to the UI, we have our familiar code to add the red reset button and set the screen black. First we see the encoder callback, which we'll come back to in a minute. At line 77, we define the encoder variable as an LVGL INDEV device. Notice its INDEV type is encoder. Then we set the encoder's callback. Back up at line 59, we'll look at the encoder's callback. The callback is fairly simple. we grab the rotary value from our driver right here. We set the data's encoder difference variable equal to the rotary value difference, which is just, in this case, val minus old val. Then we set the data state, and that occurs when if we press the button. If we press the button, the data state is set to INDEV state pressed. If we do not press the button, then it's released, and so it defaults to INDEV state released. Oh, and we update the edit label, and that's just with some simple code here, and that's purely for this demo so that you can see the difference between navigation mode and the edit mode. Okay, let's go back and look at our UI widgets. Starting in line 82, we have the definition for this first slider widget. You can see it's fairly simple. We have a bunch of style statements which I'll discuss in a second. At line 82, I have a callback for the slider's label. And all I'm doing is getting the slider's value and putting it into the label after I made it string. Now let's look at the style statements. Line 88 is setting the slider's background bar brighter by changing the opacity to 200. Next, we set the bar color to yellow using part.main. The next one is rather clever. I am setting the color of the indicator to purple, but I do this under a condition. Let's look at that. If the state of the slider is focused, then the indicator is turned purple. Otherwise, it reverts back to its default of blue. And finally, in the slider definition, you see I've added the event to update the label. And I do this under the state of event value changed, which of course will occur anytime I turn the knob and change the value. Our second slider is coded exactly the same, the only difference being its position on the screen. Now let's go to line 125. You see that I've defined something called an encoder group. After I've defined it, I add the slider as the first object and the slider 2 as a second object. And then I set this group to our encoder driver that we define way at the top of the program. Okay, that's all that we needed to do to get all the functionality that we see. I've already clicked the green run icon, so we can go back and look at the program. Okay, this time I have the first slider selected. I can press the switch button, which changes the state to edit mode. Now I can move the knob and change its value. And whenever I'm ready, I can press the rotary switch, putting it back into navigation mode and allowing me to change the widget that has focus. Notice I have the second widget focused. I can press the rotary button. That puts it in edit mode, and now I can set this widget as well. Using the edit range made the navigation rotation sluggish. I improved it by using a smaller range. Okay, let's take a look at another example. Let's stop the program. Please open test_slider_encoder in Thony. This example has a single slider. Navigation would be overkill here, but I address it. The rotary encoder is set up the same way as the first example. Let's go ahead and run the program and look at it. I click the green red icon. And now we have a single slider. Notice that its mode is already in edit. So I can just simply turn the knob, which changes the values. Okay, now that we see it working, let's walk through the code. So here's the same definitions as we had before for the import and setting up the rotary device. Again, I have the same min and max values in the same increment. I have the same reset. I have the same update edit label and the same read encoder. The same definition for the encoder device. And a very similar definition for the slider. So the one difference is in the encoder group, I've added another statement. Encoder group.editing is equal to true. By doing this, we put the encoder group into edit mode. And then we don't have to deal with the whole logic around navigation. It's already focused and selected this widget, since there's only one widget to choose. So the encoder can still provide the operating logic for the edit and tracking the values as it did before, but now it's even simpler. Hopefully these code examples help you understand the encoder operating logic. In summary, we discussed rotary encoders, wired and mounted rotaries. We uploaded the driver files. We tested the rotary encoder first, and then we reviewed LVGL example codes to see how we could use the rotary encoder with multiple devices or with a single widget. Now you should see how easy it is to include an external rotary encoder in your LVGL programs, and that it provides excellent functionality with very little code. I hope this video helps your LVGL MicroPython coding. Thank you for listening.